Below is a schematic diagram illustrating the design of the power button PMIC and CPU. The back lines shown between the PMIC and CPU provide the current required to power the CPU. In addition, the boost input lines are shown providing the primary power current to the PMIC. The capacitors or boost line are working with the VBAT line or VPH-PWR line. If we have 7 boost input capacitors, then we must have 7 bobbins or 7 buck output inductors. It is important to take note of this, so it's recommended to study it well and then to practice. The power-up cycle must start with the low current, then gradually increases as if it were a staircase. Depending on the range of the device, the current can reach 200-250 milliamperes before the image appears. This is when the PMIC, CPU and memories start to act. Charger Lab Power Z video. By pressing the power button for half a second, the PMIC is acting to deliver a current up to 70 milliamperes. In the next second, the consumption can reach 200 milliamperes without the image appearing on the screen. This means that PMIC, CPU and memory, AMIMC, all are working together to perform the power-up one, so to speak. When the image is on the screen, the peak current can reach 300-350 milliamperes. This causes the CPU to send information to the circuits to power up through I2C communication line. This causes all parts of the system to turn on and be ready to use. We can have I2C0, I2C1, I2C2 and so on lines. The current can go up to 500 milliamperes, allowing the other circuits such as image, touch, camera and audio to start working. Then we'll have the peak that will rise up to 1.2, 1.3 amperes, which means that all the circuits are working. After the peak, the current should gradually decrease. It is important that the peak does not exceed 10 seconds because a longer duration can mean a problem on the motherboard. Therefore, it is necessary to be careful so that the peak does not remain for a long period of time. When the current starts to decrease, the I2C line circuits are deactivated, causing the energy consumption to drop up to 400 milliamperes. This is the signal that the logo has started to enter and the menu has been activated. All this depends on the range of the device. This part is very important, and in this way you'll understand the power-up cycle of a mobile device. In less than 20 seconds you can already have a little idea of what failure the device has. In this graph, we can observe how the device enters energy-saving mode. We see a lower current each time and gradually it reaches 3, 4 or 5 milliamperes. This means that the motherboard has no consumption, which is very important to take it into account. This test is very important after a repair. With the help of the energy saving mode test, we can know if the customer has problems with the motherboard or with the battery. So, if our customer says that the device runs out quickly to rule out the battery, we have to do this test. You just have to connect the device to the laboratory power supply and wait for it to enter in the energy saving mode. If the device consumes very little current, around 4-5 milliamperes, it means that the problem is with the battery. If the device consumes more than 50 milliamperes, the problem is on the motherboard. The higher the current consumed, the faster the battery will discharge. Let's see this Samsung A51. We check the power button 3 or 4 times for half a second and we observe a slightly high current reaching 200 milliamperes. First, we must inspect the PMIC inputs and outputs. Then, we continue with the complete power-up cycle to see what happens. We observe peak currents of up to 1.5 ampere and then the current starts to decrease gradually. This indicates that the device is entering power-saving mode. If we press the power button, the device wakes up and the current starts to increase. Soon we'll see where the PMIC, CPU, memory and display comes into play.